Hello everyone, welcome to my channel. Today we are starting our VLSI Fundamental series. In this video, I will explain the basics of VLSI, the difference between ASIC and FPGA, how chip is made, CMOS Basics, and standard cell libraries. Let's get started. What is VLSI? VLSI stands for Very Large Scale Integration. In simple words, it means putting millions or even billions of transistors on single chip. Back in the earlier days, computers filled entire rooms had only few thousands of transistors. Today, one smartphone chip has billions of transistors. Then applications of VLSI. VLSI is everywhere in like smartphones, cars, satellites, AI processors, and medical devices. In cars, chips handle safety system sensors and navigation. In AI, specialized chips accelerate neural networks. Even your Wi-Fi router and smartwatch exist because of integrated circuits. So VLSI is not nice. It's the foundation of modern tech. Now let's go for uh, Now let's compare FPGA versus ASIC. FPGA stands for Field Programmable Gate Array. They are reconfigurable chips. You can program them anytime. They are fantastic for prototyping research, and they are consumes more power than slower than the ASICs. They are flexible and adaptable. Then we will go for the ASIC. ASIC stands for Application Specific Integrated Circuits. They are the very fast, very power efficient, but expensive to develop. Fixed ones manufactured. Example for ASICs are A series or Snapdragon processors. Well as a IC design flow or ASIC flow, designing a chip is like building a house, that is step by step. First, we will take a specification from the customers. Then we will go for the architectural design. Then we will write the RTL code by using very lower system level. Then we will verify its functionality. Then logic sense is where the RTL code is translates to gate level netlist. Then logic verification and testing. Then we will go for the physical design, where we do place and route. That is arranging those gates physically on the chip and connecting them with metal wires. Then after that we will go for the physical verification where the DRC, LVS, DFM and antenna checks have been done. After that sign off, then we will go for the fabrication process. This whole process can take months for small designs and 1 year or more than 1 year for the complex processors. CMOS Basics. At the heart of every modern chip is a CMOS technology. CMOS means complementary MOS. It usually two types of transistors together, PMOS and NMOS. MOSFET metal oxide semiconductor field effect transistor. It consists source, drain, gate, and substrate. Gate controls the current between source and drain, and this is the CMOS structure of inverter, where the top one is PMOS and bottom one is NMOS. The input is connected to both gates. If the input is zero, then output will be one. If the input is one, then output will be zero. Then NAND gate. This is the CMOS structure of NAND gate, where the PMOS and PMOS at the top, NMOS at the bottom. PMOS is parallel and NMOS is series. If the input is 0 0, then output will be high. If the input is 1 1, then output will be 0. This is the CMOS structure of NOR gate, where the PMOS is connected to series, where the NMOS is connected with parallel. The output is only high when input is both inputs are 0 0. If either one input is 1, then output will be the 0. Standard cell libraries. When we design chips, we don't draw every transistor inside. Instead, we use standard cells. Those are the pre-designed, pre-verified building blocks like inverters, NAND gates, or flip-flops. And we combine these cells to build complex circuits, and EDA tools place and connect with them automatically. In the final layout, cells are arranged in neat rows like bricks in a wall. This regularity makes chip easier to route and optimize. These are the logical and physical views of inverter and NAND gates. That's it for our VLSI fundamentals introduction. Thank you.